Yeah, good morning. In this session, I would like to demonstrate the separation of an azeotropic mixture using pressure swing distillation. As you are aware, this option of separating an azeotropic mixture using pressure swing distillation is possible only when the system exhibits pressure sensitive azeotrope. So I have taken such a system which is benzene and ethanol. The azeotropic composition is going to vary with respect to the pressure. When you have that kind of a system, it is possible to separate the mixture using pressure swing distillation. The data required for this problem, the basic data is already provided in this table. So starting with 100 kilomoles per hour of equimolar mixture of benzene and ethanol, we wanted to separate that into relatively pure components of benzene and toluene, benzene and ethanol. So let us go ahead with simulating this problem in Aspen. So define the two components that are involved in this problem, then select the method, property method, which I have selected as UniQuack RK. So before proceeding with simulation, let us check up whether the system is exhibiting pressure sensitive azeotrope or not. So I go to binary, then I would like to draw this TXY diagram, let us say at 3 different pressures, 1, 3 and 5. So run analysis. You can see the composition is going to vary with respect to pressure. Anyway, if you are not able to see properly from this diagram, you can go to the XY plot. So now you will be able to see the blue one corresponds to a pressure of 1 bar, the green one corresponds to a pressure of 3 bar, and of course the pink corresponds to a pressure of 5 bar. Remember, in this problem, we are starting with an equimolar mixture of benzene and ethanol. So if you try to take, we are at this point. So we are towards the right of the the azeotropic composition at a pressure of 3 bar. So starting from here, if you operate the column, let us say at 3 bar, we should be in a position to get almost pure benzene from the bottom product of the first column. Similarly, if you try to analyze what is the composition of the system from the top product of the first column, if it happens to fall below this composition towards the left of the azeotropic composition at any other pressure, now we should be able to get pure ethanol as a bottom product from the second column, operating that column at that kind of a pressure. Now in this example, because we are starting with 50% benzene and 50% ethanol, I would like to operate the first column at 3 bar, get pure benzene as a bottom product from the first column, and the composition of the top product with respect to benzene is less than 0.5. So you can simulate and see. So I will be using the second column at 1 bar so that I will be able to get pure ethanol from the bottom product as a pure product. The top product from the second column can be recycled back so that you will be able to separate out the given mixture relatively into pure components. Now let me go into the simulation environment. I have already created the flow sheet. I will try to explain the steps involved in this. Now I have used 2 rad frac columns. So this is the feed, fresh feed that is entering into the is going to be obtained as benzene from the first column, and the top product from the first column is sent as feed to the second column, and the bottom product from the second column is ethanol, and the top product from the second column is sent as recycled to the first column because the second column is going to operate at 1 bar, whereas the first column is operating at 3 bar. So I will be compressing it to 3 bar before recirculation. So let us look at the details of specifications for this problem. Now the feed is entering at 3 bar because the column is operating at 3 bar. I have taken a vapor fraction of 0.5, 50% liquid and 50% vapor. That means the system is between the bubble point temperature and dew point temperature. So with a flow rate of 100 kilomoles per hour as given in the problem statement, equimolar composition. Now let us look at the specifications of each block. There could be some issues pertaining to stages are given to be 30. We are using a total condenser. The reflux ratio has been specified as 3. The bottoms rate, because we are trying to take out the product benzene from the bottom, 50 kilomoles per hour of benzene is entering, so 50 kilomoles are going to be withdrawn. And the feed stream has been given to be 10, and the also is entering along with the feed stream on the same stage. So as you know, the first column is going to operate at 3 bar. Of course, I have neglected the pressure drop. We are assuming constant pressure. Be careful with this. I have taken the convergence. By default, it will be standard, but I have changed it to custom and then go into the block convergence. Expand this, options, expand this. So, block B3, right? So you need to go into convergence within the block, not the overall convergence. So click on this convergence. Now, standard, I am selecting Newton and also increased the number of iterations to 200. Some problem with respect to convergence. So to overcome, you are required to do this modification. So more or less, the specifications for the second column are also similar. 30 total condenser, bottoms rate 30. This is the ethanol flow rate that you will be able to get from the bottom of the second column, and the reflux ratio once again is 3. The feed stream is entering at 10th location, and the pressure of this column is 1 bar. And once again, you can see it is custom. So this is block B4. Within the block, there is a convergence option. So go to convergence, select Newton, and increase the number of iterations to 200. So this is what I have done as far as the two blocks are concerned. More or less the problem statement is complete. Now we need to compress it back to 3 bar. So what I have done here is isentropic compressor, the discharge pressure is 3 bar. Convergence, once again, you try to write it as vapor liquid because the feed is of vapor and liquid. Even after if there is some amount of liquid present, we don't mind. Here also increase the number of iterations. Okay. So with this, we have one more issue that you normally might be able. Sometimes in the report, we may not be able to see the mole and mole flows. So go to setup, expand this, report options, go to stream and click on this mole, mass, whatever you want to appear in your report. So with this, we are now ready to run the problem. So let me say next. Okay. There were some warnings, but still you should be able to get your results. Now you can see the mole fractions. So again, this was missing. So this is mainly because the convergence is not going to be achieved. Let me change the convergence again. Problem is only with respect to convergence. What I can do is main flow sheet. Now let me take azeotropic in both cases. You have no errors, but there are some warnings. You can probably ignore them. Let us see maybe the report or look at the stream results. This is likely to happen sometimes. Don't worry. You should be able to see stream results. I'm interested in the recycle, the ethylene and benzene, ethanol and benzene streams. Now you can see in stream. So we were able to get this on 99% benzene. Similarly, if you look at ethanol, we were able to get ethanol with 99% purity. And what about the purity of the recycle? See, you can see 54% and 45% ethanol, right? This is the mole fractions from the top product. So as you can see, probably from the diagram, now 54%, so it is towards the left of particular azeotropic composition. That's why we were able to completely separate out the given mixture. So this is only for a demonstration purpose. Now, why should I go for 3 bar? Can I do it at 2 bar? Of course, you can analyze by plotting these curves at 2 bar. So depending on the feed composition and depending on the top product composition that you will be able to get from the first column, now you need to decide on the pressures at which the two columns need to operate in order to separate this kind of an azeotropic mix. So with this, I would like to, so this kind of problems are repeatedly coming, especially with respect to rat frac column. Sometimes it is not showing summary. Normally this is not supposed to happen. Even after putting these results, sometimes it is giving this kind of a problem. In such a case, you can go to home, create report with the required data that you want. So you should be able to update that. Go to stream and select whatever streams for which you would like to see the result. See that we were able to get to the required purities of benzene and ethanol, though it is an azeotropic mixture, without using a third component. We were able to separate that by operating two columns at two different pressures. So with these comments, I would like to close this demo.